I'm going to say some words about telescopes and the technology of telescopes. But you should keep in mind that the only thing telescopes really do is to extend and greatly amplify our ability of things we could, in principle, see with our eyes. And although the telescopes are technology that leads to great discoveries, I'll talk about some of them, it is really, of course, the people who make the discoveries, and the telescopes and the technology enable the discoveries. So the telescope first came into use a little bit over 400 years ago. Historians argue about who invented the telescope. The only thing they agree on unanimously is that it wasn't Galileo Galilei. Galileo didn't invent the telescope, but neither did he ever deny inventing the telescope. When writing about his discoveries, he would write, he didn't use the word telescope. The telescope was a word coined by Johannes Kepler, another astronomer. Galileo called it an optic tube. He said, I used an optic tube devised by myself. So he didn't really claim to have invented. Devised is slightly different than invented, but if you thought he invented it, when he said he devised it, you would have think, yes, he did invent it. One of the things I'd like to stress is how crude the early telescopes were, the telescopes that were used by Galileo. If you go to the Museum of the History of Science in Florence, you'll see telescopes that were attributed to Galileo, that they believe Galileo used. When Galileo first used the telescope, his telescope magnified objects by about a factor of 3. And he had an extremely small field of view. The best telescopes Galileo ever used could magnify by about a factor of 20 or 30. So you can get a much better optical instrument for $5.95 in a drugstore than Galileo ever had. However, with this small advance in technology, this small extension of the human vision, allowing Galileo to see objects that no one had seen before, just this small extension of the human vision. And within a year or two, Galileo had made 8 truly remarkable discoveries with the telescope. He discovered spots on the sun and proved that sunspots actually were on the surface of the sun. Macchie solare, it was the Italian description he used for sunspots. When you have a macchiato next time, it's Italian for stain. You can think of the stains on the sun. Galileo proved that the imperfections we see on the moon, the discolorations, were actually mountains on the moon. It was thought that the moon's surface was perfectly smooth, and it might be discolored like perfectly smooth marble, but it was created by the divine being, so it had to be perfect, it had to be smooth. Galileo proved that that wasn't true. With his primitive telescopes, Galileo discovered the phases of Venus. The fact that just as the moon goes through the quarter moon, the half moon, etc., Venus also goes through phases for the same reason. Galileo discovered the rings of Saturn. His telescopes were not powerful enough or sufficient to discern that they were rings, but he could tell that Saturn was a planet that was not round. And he described Saturn as a planet with ears. He discovered the rings of Saturn. He discovered that stars are more distant than planets. When he looked at planets through his telescope, they looked larger. When he looked at stars through his telescope, they looked just the same. They looked like stars. Galileo discovered that there are stars invisible to the naked eye. This was a tremendous discovery that shook people up. Why would there be things in the universe that humans can't see? It was a remarkable discovery. Galileo discovered that the Milky Way was made of stars, and finally Galileo discovered the moons of Jupiter. This is with extremely crude astronomical telescopes. Some of Galileo's contemporaries said that they were amazed that Galileo discovered the moons of Jupiter, but they were also amazed that he could look through his telescope and actually find Jupiter. Well, telescopes were invented in the 17th century, and there are two main types of telescopes. The refracting telescope, and I'll put Galileo in quotes here, although he didn't use that, he didn't invent it. He took advantage of it like no one did. And this involves two lenses, and there's reflecting telescopes that were invented by Isaac Newton in 1668, which uses a parabolic shape of either a mirror or a polished piece of glass. Well, the world's largest refracting telescope that uses lenses, is not far from here on the shores of Williams Bay, Wisconsin, Yerkes Observatory, operated by the University of Chicago. And I'd like to invite you to go out and visit it sometime. There have been quite famous visitors who have stood there. You can stand where Einstein stood. And the telescope looks pretty much like this today. Now, this telescope is not very useful anymore for astronomical research because it's in Wisconsin. Not that I have anything against Wisconsin. Some of my best friends actually are cheeseheads. But it's at essentially sea level, cloudy, grass, people, light pollution. The best telescopes now are on mountains in high desert areas. And the largest telescopes are not refracting. Today, the largest telescopes are reflecting. This is two images of the largest telescopes today. One of them is in Arizona. It's the Large Binocular Telescope, which consists of two 8.4 meter, about 10 yards in diameter, mirrors. And another is a 10-meter telescope that's on the Canary Islands that was built by Spain. These are the largest telescopes in use today. So there are about 17 telescopes that are either almost as large or almost as good as these, and they are spread throughout the world, but most of them actually have to be built in regions of the world that are high, dry, and dark. I'm afraid the lights in here are a little too bright for you to see that image. This is an image of the Earth as taken from space. And you see that if you're looking for a place that's dark, away from light pollution, you wouldn't want to put really a telescope in the US or in Europe or in Japan. If you want to be high, dry, and dark, the best place to go is Chile. Chile is high, dry, and dark. It's a developed country with infrastructure. It's accessible, stable politically, and it borders the Pacific Ocean. And the weather in Chile is very good and very calm. So Chile is high, dry, and dark. This is an image of some telescopes I'll talk about in a minute that are owned by the Europeans. And you can see that it is high. It's in the Andes, in the Atacama Desert, one of the driest places on Earth, and it's dark because there's no one living around there. So never buy an observatory where you can see a tree. What you want to look out is to see hundreds of square miles of landscape that looks like kitty litter. Then you know it's a good place for a telescope. This is a close-up image of the very large telescope array that the Europeans built in Chile, the European Southern Observatory, at an altitude of close to 9,000 feet. This is probably $1.5 to $2 billion worth of telescopes there. It's a very elaborate and expensive infrastructure. And in the US, we say that this is the way God would build observatories if he had enough money. The telescope that's used by members of our department are the Magellan telescopes, which are also in Chile, not that far away, and they're two 6.5-meter telescopes at Las Campanas, Chile. So our astronomers from our department and other departments throughout the country go there to use them, and it's very interesting to go there. You see some sort of interesting creatures when you go there, and you have to be careful in the dorms to shake out your shoes because there's no telling what might have crawled in there. These telescopes use tremendously large mirrors. Now, the objective lens of Galileo's telescopes were only about this big. Now they are 8.5-meter mirrors. And just to give you an idea of the size of the mirrors, we had a very small person stand up next to the mirror to give you some idea of the size. This is the back of the glass. The other side of it is luminaries. And I thought I'd say a word about the technology of how these mirrors are made. Now, we're familiar with, at Chicago, with the use of a football stadium to do science. Just a few blocks from here on Ellis is where Enrico Fermi used the football stadium of the University of Chicago, Stagg Field, to build the first self-sustaining chain reaction. Well, these mirrors are also made in a football stadium, under a football stadium, and the football stadium where they're made is at the University of Arizona. So I have this idea that 200 years from now, when people are writing the histories of universities, they'll say they built these enormous stadiums for the purposes of science, and when they weren't being used on Saturday, they played some insignificant sport. Underneath the stands of the University of Arizona Stadium is the Mirror Lab at the University of Arizona, and this is where they cast and polish and make these enormous mirrors. It starts off, this is the mold of the mirror that people are standing in, and what they're doing is stacking the back of the bottom part of the mold with a ceramic, an aluminosilicate ceramic, that will be removed after the mirror is cast to make the mirror lighter. Then they put 20 tons of borosilicate glass in the mold, and then they cover it up, and they have to heat the glass to melt it to a temperature of about 2,000 degrees, and the mirror has to be a parabolic shape. So if they would just make the mirror, then they'd have to dig out all of the glass to make the mirror parabolic. So to get an enormous start on that, they spin the mirror when the glass is liquid. And the spinning mirror forces the glass to take roughly a parabolic shape. So they have this enormous oven that's at a temperature of 2,000 degrees, spinning at 8 times a minute. It's a remarkable thing if you ever have the opportunity to see it. And if you put a camera inside the mirror cell, as the glass melts, it reaches a temperature of about 2,000 degrees. This is an image just before it melts. And when I say it melts, it reaches the consistency, say, of cold honey that you would take out of your refrigerator. Then the mirror is removed, and it has to be polished to have as close to a perfect parabolic shape as possible. So the mirror has to be polished, and the bumps in the mirror have to be controlled to be smaller than about 1/1,000,000th of an inch. Now, to give you an idea of how small 1/1,000,000th of an inch is, these are 8.5-meter diameter mirrors. If we would imagine a mirror as large as the US, then you would allow bumps that are no larger than 1 inch. So you would have to go to an area the size of the US and smooth it, make it perfectly flat like the Midwest or something, where the bumps are no more than 1 inch. It's a remarkable thing. So this is how these largest mirrors are made in the technology of telescopes. Now, in terms of the growth of technology, just as in the speed of computers or the power of accelerators, it is a logarithmic growth in the aperture of the telescope. The aperture is how large it is, the size of it. Starting with Galileo in the early 1600s up to just a few years ago, every 30 years or so, the size of the largest telescopes double. Again, this has been true roughly since the time of Galileo till today. Every 30 years, the size of telescopes double. So we think it is, see, this is the same slide, I guess. We think that it is time to take another step and build a larger telescope that would be roughly 2 or 3 times larger than the largest telescopes today. There are 3 projects in the world that are attempting to do this, 2 of them led by U.S. Universities and institutions, and 1 led by the Europeans. The telescope that we're involved with, which is an example of this, is something known as the Giant Magellan Telescope, and it uses 7 of these enormous 8.5-meter mirrors. And to give you a scale, this is a human that's standing there. So this will be the next generation of telescopes that we feel will be on the air in 2020. On January 14th, 2020 is when it will see first light, something like that. So these telescopes, compared to the Hubble Space Telescope, will take images that are 10 times sharper. So many of us, many of you have been amazed by the beautiful pictures sent down by the Hubble Space Telescope. These images from this telescope will have 10 times the resolution, 10 times the number of pixels, 10 times sharper than the images from the Hubble Space Telescope. It will also have a collecting area that's 100 times larger than the mirror on the Hubble Space Telescope. It will have a collecting area equivalent to 5 million human eyes looking at the same point in space. So it will be a remarkable advance in the technology of telescopes. And in terms of the technology, one of the remarkable advances that have allowed us to build large telescopes on Earth has been something known as adaptive optics. Until about 20 years or so ago, it was thought that if you really wanted to make high-resolution, sharp images of astronomical objects, you had to go into space. You had to go above the atmosphere, because astronomers do not like the atmosphere. They don't want to live on a planet with an atmosphere, because the atmosphere distorts the image of objects that are out in space. However, 20 or 25 years ago, it was realized that we can correct for the distortion of the atmosphere by something known as adaptive optics. And the way this works is they're at an observatory, will fire a laser beam into the sky with a certain wavelength of light that will excite sodium atoms in the atmosphere. About 90 kilometers, about 60 miles above us, there is a layer in the atmosphere that's rich in sodium. And as the laser goes up there, it makes an artificial star in the atmosphere of the sky, in the atmosphere of the Earth. Then, if we can somehow change the shape of the mirrors a little bit, we can compensate for the blurring of the atmosphere. So there are thousands of little actuators on the back of these mirrors that slightly deform the mirrors, making up for the distortions caused by the atmosphere. Now, this is a great technological breakthrough that was made 25 years or so ago by the military. But eventually astronomers learned about it and developed it, and now it's used routinely in astronomy. So to give you an idea of these giant telescope projects, no one institution can afford to build a telescope. This is about a $700 million telescope. $700 million, that's with tax tip, dealer prep, rust proofing, everything included. But it's still beyond the means of any single institution, so other consortia of institutions get together and build these telescopes. It's likely that this one will be built without the use of money from the US government. It will be built completely by private means. Now, when I've spoken about telescopes, I've talked mostly about telescopes that are optical telescopes, that are sensitive to the type of electromagnetic radiation we can see with our eye. But of course, we learn about the universe using much more than optical wavelengths. We use millimeter wavelengths. For instance, these are just some of the observatories used by the University of Chicago astronomers, an observatory known as CARMA in California, the Combined Array for Millimeter Wave Astronomy. It's radio telescopes. Gamma ray telescopes in Arizona, cosmic microwave background telescopes in Chile. We are building a detector that will fly in a 747 above a lot of the atmosphere. We cut a hole in a 747. Don't try this at home. And it gets above much of the atmosphere, and this is infrared radiation. There is large cosmic ray experiments in Argentina, satellites, and my colleagues spend a lot of December, January, and February at the South Pole doing experiments in radio astronomy at the South Pole. So they can leave Chicago in January and go to a place that's much colder, something that is a challenge. So in addition to the wide array of telescopes and new technology on Earth, we have technology in space, the Hubble Space Telescope, the Compton Gamma Ray Telescope, the Fermi Gamma Ray Telescope, the Spitzer Telescope, and the Chandra X-ray Observatory. And if I can brag just for a minute, Hubble was a student at the University of Chicago, Fermi was a professor, Chandra was a professor, and Compton was a professor at the University of Chicago. The only great observatory not named for someone from Chicago is this one, named for Elliot Spitzer. I'm sorry, it's Lyman Spitzer. He was a professor at a small liberal arts institution in New Jersey. The College of New Jersey or something like that. So I've described some of the tools and the remarkable advances in technology that allow us to view the universe in ways that are just amazing, just the information we get. And what I'd like to do now is to tell you just two of the fields that are advancing rapidly that uses the information and the results from this remarkable technology of telescopes. First of all, I'd like to tell you about the field and the advances in cosmology. Now, I am a cosmologist, not to be confused with cosmetologist. There's more money in cosmetology, actually, than in cosmology. But cosmology is a study of the universe, the origin, the evolution, and the large-scale structure of the universe. There was an American anthropologist, George Murdoch, who surveyed all of the societies, both prehistoric and historic, that were known. And what George Murdoch did was to look for things that he called and described cultural universals, things that every society has. And among these were religious rituals, body adornment, marriage taboos. I guess body adornment is cosmetology, so it was there too. Marriage taboos, alcoholic beverages, and cosmology. Every society has had a cosmology, a view of the universe. And I think all societies, is part of human nature to look up in the sky and wonder what's up there. How old is it? Where did it come from? What does it mean? How does it relate to myself? So I think we are all born to be astronomers. We are all born to be physicists. Oops. So, we are all born to be Einsteins. Einstein said the most beautiful thing we can experience is the mysterious. To him, the mysterious was the source of all true art and science. He thought that those who are a stranger to mystery are as good as dead, their eyes are closed. So when we look up in the sky, we ask questions about it and try to understand the mysteries of what we see in the sky, and that is what cosmologists do. So, cosmologists do more than just try to see what's in the sky. We try to poke our heads through and try to understand the machinery that underlies the movement of things in the sky, how the universe works. We just don't want to see what's in the universe, but how actually it works, how it relates to the laws of nature, to try to understand the age of the universe, the origin of the universe. This is all part of our attempt to understand our place in the universe. I think much of humanity's deal with the answer to the question, what is our place in the universe? And throughout history, our perception of what is the universe has influenced our attempts to answer the question, what is our place in the universe? If I had been giving this lecture 100 years ago, in 1911, I would have described a much different universe than we know exists today. I would have described that the entire universe is about 30,000 light years in diameter and about 6,500 light years in thickness, roughly the size of our own Milky Way galaxy. It was thought that there was one galaxy in the universe and we are living in it. 100 years ago, an astronomer would have told you that we live at or very near the center of the universe. Now we know that we do not live at or near the center of the universe, and in fact, the universe has no center. We would have said that space and time are absolute, not relative, that the universe is static, unchanging in time, that it is eternal, it's always existed, and that the composition of the universe was stars in the hood. All of these things I would have told you about the universe 100 years ago turn out not to be correct. For instance, we know that we do not live in the center of the universe. We live on a distant spiral arm of the Milky Way galaxy, 30,000 light years from the center of the galaxy. So we live out in the far distant suburbs. Technically, it's the Schaumburg of the galaxy. And we are not at rest in this galaxy. We're orbiting about the center of the Milky Way at a velocity of 450,000 miles per hour. In 1924, Edwin Hubble discovered that the Milky Way is not the only galaxy in the universe, that these nebulae that have been seen by astronomers since the time of Galileo were island universes, like the Andromeda galaxy, that's 2 million light years from our Milky Way galaxy. And the Andromeda galaxy, we are not at rest with the Andromeda galaxy. We're heading toward a head-on collision with the Andromeda galaxy at a velocity of 90,000 miles per hour. We learned in the 1960s that there are larger structures in the universe than galaxies. There's clusters of galaxies, like the Virgo cluster of galaxies, 50 million light years away. The Hydra supercluster of galaxies, 500 million light years away. All these enormous structures are pulling on our poor defenseless little galaxy, pulling us through space, and now we're not at rest. We're traveling through space right now with a velocity of 1,400,000 miles per hour. So our conception of our place in the universe has been changed in the 20th century. Also, the idea that the universe is unchanging and eternal changed with the discovery of Edwin Hubble that the universe began with a bang. And Hubble was able to make this discovery because he had use of a great telescope in 1910 and the 1920s, the Mount Wilson 100-inch Hooker telescope. And again, the discoveries are not made by telescopes, they're made by people. This is a photograph of Hubble looking through the 100-inch Mount Wilson Hooker telescope. So our conception of the universe has changed, and now we view the universe within the framework of the Big Bang. And within this idea, our universe emerged from a state of high temperature and density 13.78 thousand million years ago last Tuesday. And it's expanding and cooling, evolving and dynamic. Now, this is known as the Big Bang Theory. And some people say, well, it's just a theory. But there are different senses to the word theory. There are theories of crazy things, theories of the Loch Ness Monster, theories of this and that. That's one sense of the word theory. But when we talk about the Big Bang Theory, we mean it in another sense. That's actually the primary sense of the word theory. In the Oxford English Dictionary, it's a statement of what are held to be the general laws, principles, or causes of something known or observed. So it's not just something random, it's something that is observed and is the general principles of something that is known. So the Big Bang is actually more than a theory, much more than a theory. It's a television program. So it's something we have to take seriously. According to the Big Bang Theory, we live in an evolving universe. Now, I have friends who are paleontologists who tell us that life on Earth evolves, and that 70 million years ago, there were giant dinosaurs walking around Earth. Now, they have to dig up fossils and things to try to piece this together, but astronomers have a big advantage because if we want to study the evolution of the universe, how the universe changes with time, we don't have to dig up fossils. We can use time machines. We have time machines. The time machines we use are telescopes. Because of the finite velocity of light, as we look out in space, we're looking back in time. Things that are farther away appear to us to be older than things that are closer. That's why often when I give a lecture, people in the back of the room seem a little bit younger, usually, just typically, than the people in the front. As we look out in space, we're looking back in time. So we can use telescopes to trace the evolution of the universe, to actually look through the telescope and see that the universe is changing. The evolution of the universe is not a theory. You can look through a telescope and see it. Now, some people still don't believe that, just as people refuse to look through Galileo's telescope because they already knew the answer. One of the things we learn, I just mentioned two of the questions now that when I come back 100 years from now and give this talk, I'll say might be different. One of the things we learn in the evolution of the universe is the present composition of the universe. What is the universe made of today? And there are various things that we know about. We know that there's radiation in the universe, but it only makes up 0.005% of what's in the universe. We also learned that chemistry is not very important. I don't know why we have a chemistry department. It's only 0.025% of what's in the universe. Neutrinos are much more important in the universe. Stars, hydrogen and helium gas. But if we put together everything that we see in the universe that we know about, it's only 5% of what's in the universe. And our telescopes suggest to us that 95% of the mass and energy in the universe is unknown. dark matter holding galaxies together and other large-scale structures, and dark energy pushing these structures apart in the cosmic expansion. Maybe 100 years from now, we'll talk about a multiverse. The fact that the universe that we see now is just one universe in a much larger structure known as a multiverse. And this may have something profound to say about the beginning of the universe. Perhaps the universe has no beginning and will have no end, that it's eternally self-reproducing. This is one of the questions we're trying to answer by looking through telescopes. Now let me turn and talk about things that are very nearby that we're learning about with telescopes, and that is exoplanets, planets orbiting about other stars. First, let me remind you about the astronomy and planetary astronomy you learned in school. You learned in school that there are 8 planets. Actually, you probably learned there are 9 planets, but Pluto unless you went to school before 1930, and then you would have learned that there are 8 planets. But Pluto has been voted off the island. Pluto is not considered a normal planet. It's called, well, it used to be called a dwarf planet, but recently it's been decided that that's not a polite thing to say, so it's known as a size-disadvantaged planet. It's a more politically correct description. And there'll be hundreds of objects like Pluto out there. So if we want the solar system to remain exclusive, we have to exclude Pluto. So there are 8 planets, and they're divided into 3 types. Everything's divided into 3 types, right? Astronomers are divided into 3 types. There are those who can count and those who can't count. But planets are divided into 3 types. There's my favorite type of planets, my very favorite type of planet, the rocky planet. I live on one. Mercury, Venus, Earth, and Mars. Then there are the gas giant planets like Jupiter and Saturn, and there are ice giant planets like Uranus and Neptune. Now this diagram, of course, shows you some nice pictures of the planets, but it's not to scale. This is something that will give you some idea of the scale of the solar system. First of all, the distance from the sun to the planet is usually given in a convenient unit known as the astronomical unit, or AU. An astronomical unit is the distance between the sun and the earth, or about 93 million miles. So Mercury and Venus, or interior, have a smaller distance to the sun than Earth, 0.4 and 0.7 AU. Earth is at 1 AU. Mars is 50% farther away from the sun than Earth. Jupiter about 5 AU, Saturn around 10, Uranus at 19, Neptune at 30. So it takes light 4 hours to reach Neptune. So Neptune is 30 times farther away than Earth. There is no way I can have a diagram. Neptune would be on 64th Street or something like that if I had the diagram to scale. I'll also say a word about the average temperatures in the solar system. The average temperature of Mercury is 1,000 degrees. It's too hot for me. The average temperature of Neptune is minus 350 degrees. That's too cold for me. I'm sort of like Goldilocks. I like to be in the zone where it's not too hot and not too cold. The average temperature on Earth is 59 degrees. Earth is in a habitable zone, for me at least, around the sun. Now, exactly how far from the sun the habitable zone will be depends upon how far from a star depends upon the size of the star and how bright it is. So with our sun, you could imagine living on a planet that's about the distance somewhere between Venus and Mars from the sun. But if the star is smaller and not as bright, not putting out as much energy, you can live closer to that planet and still live in the habitable zone. So this is the mass of the star in solar masses, and the distance from the star of planet, again in astronomical units, and this shaded area is what we think the habitable zone might be. So in our solar system, the habitable zone is around the distance from Earth. Around another star, like Gliese 581, which is a smaller star, the habitable zone will be closer. Okay, so before 1995, we knew of 8 planets. They were all in our solar system. Since 1995, there has been 697 confirmed discoveries of planets around other stars. Before, many of you remember 1995. We didn't know of any. Now we know of nearly 600. And I can give you a list of 1,235 candidates. And statistically, over 1,000 of these will turn out to be planets. And 54 planets are possible rocky planets. We see all sorts of planets. I'll talk about super Earths. Rocky planets that are much larger than Earth. Hot Jupiters. Planets that have masses equal to or larger than Jupiter, but are much closer to their star. Water worlds. Carbon worlds. Worlds that seem to be made of carbon. Our Earth is mostly silicon. We are a carbon-based life form on a silicon planet. Perhaps there are silicon-based life forms on carbon planets. We see planets in systems with 1 planet, 2 planets, 3 planets, 4 planets, 5 planets, 6 planets. That's all we've discovered so far because we just too hard right now to see systems with larger numbers of planets. And we see planets in stars or orbiting about stars that are sun-like stars, stars bigger than the sun, smaller than the sun, younger than the sun, older, brown dwarfs, white dwarfs, binary stars, and neutron stars. We see planets just about everywhere we look. Now, how do we see and discover a planet around another star? Well, we use a telescope. Now, planets are smaller than the stars and not very bright. So looking for a direct image of a planet around another star is trying to take a picture, a photograph of a firefly next to a searchlight. What you have to do is to somehow block out the light from the searchlight. And this is what is done by adaptive optics. So this is the direct image of a planetary system around the star HR 8799. These would be wonderful names for these stars, HR 8799. And it's a star that's 130 light years away. And if you're looking for a planet, you can't look too close to the star, and this planet has to be very large, so you're biased to look for large planets that are far from the star. This junk in the middle and all these black splotches here is because of the incomplete subtraction of the light from the star. The star is millions of times brighter than the planets. We have to remove the light from the star. It can't be done perfectly. But this is a system with 1, 2, 3, 4 planets orbiting about this star. And that illustrates 20 astronomical units. So these are about the distance of Uranus. We can't see Earth-like rocky planets close to that star because it'll be in the glare of that star. Again, we are biased to see planets that are large and far away from the host star. We can also discover planets not by directly imaging the planets, but by seeing the effect of the planet as it orbits around the star on the velocity of the star. As the planet orbits around the star, it causes the star to wobble. If we measure very carefully the light from the star, we can determine the velocity of the wobbling by the Doppler effect. And again, we're most sensitive to very large planets, which will move the star more, that are closer to the star because it will have a larger effect. We can also discover planets through the transit technique. If we look at the light from a the light from a star very carefully, if there is a planet that passes in front of the star, it's going to block out a little bit of light from the star. So as we measure the apparent brightness of the star, as the planet passes in front of it, the star will appear just a little bit dimmer. This is a very small effect, and it's best done from space. And there's been a satellite that the U.S. launched a few years ago that's done remarkable work, the Kepler satellite. And to do things in space is expensive. Money weighs less in space. This was about a $1 billion satellite. So what we've discovered are planets that are effectively more massive than the Earth, because the smaller mass planets are harder to see, and planets that are closer to their host star, because if it's far from the host star, it has a smaller effect on the host star. Except for these out here, these were the ones that were discovered by direct imaging. The different colors correspond to different techniques for discovering the planets. These are 4 planets in our solar system: Venus, Earth, Jupiter, and Uranus, to see where they would go on this graph. So we're not yet at the point where we can look out into space and see another star and detect planets like our own solar system, because we're most sensitive now to planets that are larger and planets that are closer to the star. But we're getting there. But we've discovered a remarkable variety of planets around other stars. We see gas giants like Jupiter. This is a graph of the size of the planet in units of the size of the Earth, and the mass of the planet in units of the mass of the Earth. So we see gas giants like Jupiter. Some are much more massive than Jupiter. Jupiter and Saturn are here. We see ice giants like Neptune. This is Uranus and Neptune. We see planets like Neptune. And we see rocky planets like Earth. Let me show you images, not images, but drawings of what some of these discovered planets. One of the planets is Kepler 10b, which is a hot exo-Earth. This is about the smallest planet that's been discovered. It has a radius of 1.4 times the radius of the Earth, so it's 40% larger than the Earth in radius, but it's 60 times closer to its host star, so it's very hot. It's a hot exo-Earth. This is a planetary system around a star, a planet around a star that's 600 light years away. Now, as planets orbit about the star, if they're close to the star, they will be tidally locked, and their rotational period will be exactly the period, their orbital period. So on this planet, 1 year would equal 1 day. Now, as the planet passes behind the star, it's bright. We're seeing the bright side of the planet. As it passes in front of the star, we're seeing the dark or the cold part of the planet. So on this particular planet, HD 189733b, which is a hot Jupiter around a star 200 light years away, we can make a map of the temperature of that planet. We can determine the temperature of the planet and the map of where it's hot and where it's colder. And we see that the hot spot is not at the exact center where it's expected, and that's because there are winds on the planet that convect the high temperature part away. So we know something about the weather on this planet. And to me, it's remarkable that there is a planet around a star that's 200 light years away. We can't even see that star with your eye. You need a pretty good telescope to see that star. And I can tell you the temperature and the winds on that planet. Now, I'm a scientist, so I don't read very many articles and put them down and say, that is really cool. But to me, knowing the weather on a planet that's 200 light years away is pretty amazing. We can learn something about the atmospheres of the planets because if the planet passes in front of the star, the light from the star will pass through the atmosphere of the planet, and the light from the planet will be absorbed, and we can determine what the atmosphere is made of. And one of the results of this has been study on another planet, GJ1214b, easy to remember, which we think is a water world. So this is a planet that's around a star that's 40 light years away. It's a relatively small star. This would be compared to the size of our sun. It's a relatively small star. It's a relatively large planet. This would be Earth, the size of Earth compared to the size of this planet. So it's 2.7 times the size of the Earth, but it seems to be a water world, a world that consists of about 50% water. Now, most of the surface of the Earth is water, but it's a rather thin layer of water on the surface of Earth. Water only makes up 0.06% of the mass of the Earth. This is a world that's mostly water. So if we're running out of water, this would be a good place to go to. Again, we know something about the surface of this planet that's 40 light years away. Another cool thing we've learned is about a planet, Kepler 16b, which is a planet that orbits two stars. Most of the stars in our galaxy are in binary systems. This is a planet orbiting about a binary system of stars that's 200 light years away. And if you were standing on the surface of this planet, you couldn't do it actually, it's a giant gas planet, but like Luke Skywalker, you would see suns set of two planets, and of two suns, of two stars, and we know something about the spin and the orientation of one of those stars. Again, something that's pretty amazing. We have seen planetary systems. We know of 115 systems that have two planets, 45 that have 3, 8 that has 4, 1 that has 5, one that has 6. As technology improves, we'll learn more and more about these multi-planet systems. And the idea that we know of a planetary system that has 6 planets in it was quite a remarkable discovery and made the front page, the cover story of Nature magazine. This Kepler 11 system is around a star. It's a more compact system than our solar system. All of the 6 planets would be, in comparison, within the orbit of Venus. So these are the relative sizes in our solar system. These are the relative size. That is the relative size of the Kepler 11 system. All right, let me again tell you, in 1995, we knew of exactly 0 planets around other stars. Now we know of nearly 700, and in a couple of years we'll know a couple of thousand. What will be in the future, we can look into the crystal ball and predict what the next few years will bring. We are on the verge of discovering moons orbiting other planets. These carbon planets, on the carbon planets, diamonds are abundant. There'll be diamond boulders. Glass is rare. So if you are a creature living on that planet, the thing that's valuable is glass, diamond is worthless. We will discover one of these planets. My proposed name for it is Planet Bling. We can look into the technology as it's being developed. In a few years, we will have the technology to discover Earth-like exoplanets around solar-type stars. Sooner or later, we will discover Earth-like exoplanets in the habitable zone around solar-type stars. With the Giant Magellan Telescope, we will take low-resolution images of Earth-like planets around other stars. We will be able to take the spectrum of the atmospheres of these Earth-like exoplanets. We will know what kind of molecules and things are in the atmosphere. We can look for biological markers. And in the next 20 years, I'm confident we will have discovery of life elsewhere in the universe. And eventually, we'll have high-resolution images of these pale blue dots that are Earth-like planets around other stars that there's evidence of life. So if I can wind up, telescopes are technologies in the search for our cosmic origin, our cosmic fate. What is the ultimate fate of the universe? The size of the universe, the age of the universe. Generally answers to the question, what is our place in the universe? What is our cosmic history? And finally, the question, are we alone in the universe? In the past 400 years, we've seen remarkable advances in the technology of telescopes. The technology advance is accelerating. Now, it could be that it will come to an end, but I don't think so, because I think we are born to explore the universe. And if I can end with a quote by our alumnus here, Edwin Hubble, the search will continue. The urge is older than history. It is not satisfied and will not be suppressed. Thank you. Are people allowed to ask questions? I may not answer them, but they're allowed to ask them. In the front there.
You started this out with 5 things, theories that were believed 100 years ago. What are your predictions for 1 or 2 theories that you take for granted today?
So I'll repeat the question. So I started out talking about the view of the universe 100 years ago and things that we thought we knew or understood about the universe that turned out not to be true. One of the predictions that I'm most confident making is that there will be surprises and there will be big changes in how we view the universe. I think that 100 years from now, we'll have evidence that our universe is not alone, that there are multiverses, that there are other universes, maybe with different numbers of dimension, might look much different. That's something that we will, I think, have evidence for in 100 years. And if I really knew how our view of the universe would change, I wouldn't be here talking about it. I'd be in my office writing about it. But it's a very good question. Yes, sir.
I'm very interested to hear your take on the recent data found by one group indicating that particles apparently travel fast.
Okay, the question has to do with a recent report of particles, neutrinos in fact, that travel faster than the velocity of light. So this report comes from an experiment in Italy, in the Gran Sasso Tunnel. It's east of Rome. And they produced neutrinos at CERN in Geneva, Switzerland, and it passes underground, and they're detected in this tunnel in Italy. And what they've discovered is that trains run slowly in Italy, but neutrinos seem to run faster than the velocity of light. So I've read the paper, and it's a very difficult experiment to do. The neutrinos arrive 62 nanoseconds, 62 1 billionth of a second sooner than they should. And I think that the answer will be something that we don't understand the production of the neutrinos at CERN or exactly in the detector how they're detected. I don't think neutrinos travel faster than the velocity of light. One reason I say that is that in 1987, in the Large Magellanic Cloud, which is about 150,000 light years away, a star exploded. Actually, the star exploded 150,000 years ago, but we saw the light from the stellar explosion, and we detected neutrinos from the stellar explosion. If those neutrinos traveled faster than light at the velocity this experiment suggests, the neutrinos would have arrived before the detector was built. So I think there's something, if not wrong, something that's not quite understood in the experiment, but stay tuned. Sure. I didn't say anything about the James Webb Space Telescope, which is being built now and will be the successor to the Hubble Space Telescope. The James Webb Telescope is not an optical telescope, it's infrared. And it's important to do this in space because infrared light in this wavelength cannot go through the atmosphere, so we just can't do it from Earth. This will be a remarkable telescope that eventually will have an impact in science and in humanity as large and comparable to the Hubble Space Telescope. It is very expensive. As I said, money weighs less in space. I don't remember the exact cost. It's $6 billion or so. Small chump change, but and in times of self-imposed austerity in spending, this is on the chopping block, and people are asking the question, can our country afford to build this telescope? The fact that we've already spent 4 or 5 of the $6 billion doesn't enter into this discussion. I hope it's built. It will do great science. It will change our view of the universe. It will do great work in exoplanets and in cosmology. And I hope we don't stop being explorers in this country. Ms. Alec.
Rocky, what is the current status of the search for dark matter?
Okay, the question is, what is the current status on the search for dark matter? Most of the mass of the universe is invisible. We don't know what it is. And there are theories that it could be a new, yet-to-be-discovered elementary particle. I think the best way to discover it is in high-energy accelerators like CERN in Switzerland. They're looking, but it's next on the list to do after they discover that damn Higgs boson. We got to get that out of the way. Yes, sir.
Can you explain the connection or derivation of the Magellan telescope with the name uses?
So it's named the Magellan Telescope because the Magellanic Clouds are right above the telescope. And we'd love to name it after someone who gave a few $100 million to build a telescope. That possibility is still there for the giant Magellan Telescope. But it's because of its use in looking at the Magellanic Clouds. Let's see, I'll take one more question. Yes, sir.
Mauna Kea.
I'm sorry, say again?
Mauna Kea in Hawaii. Are they doing anything significant up on Mauna Kea?
Oh, and on Mauna Kea in Hawaii. Other than Chile, Mauna Kea, Hawaii is the best place to build telescopes. That's where the Keck telescopes are. I've showed pictures of the Keck telescopes. And in addition to the giant Magellan telescope, there's another project that's mostly led by California institutions in the US to build a telescope like the Giant Magellan Telescope on Mauna Kea in Hawaii. So I think it would be great to have two telescopes that the US build, one that Europe builds, and I hope both the Giant Magellan Telescope and this Hawaii telescope are built. I don't think technology will end. We're not satisfied, and we will not be suppressed. Thank you very much.